Today we will discuss why physicists are looking to create and capture multiple Higgs bosons simultaneously at the Large Hadron Collider. What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a brilliant week and have a fantastic weekend in store. Now today, we're going to be discussing why LHC scientists are looking to create, capture and study multiple Higgs bosons simultaneously at the Large Hadron Collider. The Higgs boson was discovered in 2012. However, there are still many open questions related to the Higgs boson and the underlying Higgs field. The mechanism underlying the Higgs field predicts that the field can interact with itself. In other words, a single Higgs boson can decay into two Higgs bosons. This may not seem like a particularly important revelation, but studying these self-interactions could tell us a great deal about the nature, past and future of the universe we live in. Multi-Higgs interactions can help us to map the shape of the Higgs potential, which in turn controls the energy density of the universe. Understanding the shape of this potential could illuminate how the universe developed an excess of matter over antimatter, and hence why we're here, and also shed light on how the universe may end, potentially with us quantum tunneling to a lower energy vacuum. Numerous beyond standard model physics hypotheses also suggest that the production rates of di-Higgs or n-Higgs interactions should be boosted relative to the baseline rates predicted by the standard model. So if physicists can capture a significant number of Higgs bosons bashing off one another, they may find signposts for where new particles and new physics are hiding. Producing multiple Higgs bosons in LHC interactions and at future colliders will help us to understand why we are here and where we're going. To help me dig into the current status, challenges and exciting future of multi-Higgs work at the LHC, I'm joined by a brilliant special guest, Dr. Tristan Du Pree. Dr. Du Pree is a particle physicist at NICEV, the National Institute for Subatomic Physics in Amsterdam, Netherlands. He is a member of the Atlas collaboration at the Large Hadron Collider and has conducted research in multiple areas, including multi-Higgs work. Tristan also blogs about cutting-edge particle physics research for New Scientist and is an active science communicator. So I couldn't hope for a better special guest to help me understand the importance of juggling multiple Higgs bosons simultaneously. Let's start from the top. What are we talking about when we say di-Higgs events or interactions or n-Higgs interactions? What are we talking about here? Because we usually talk about producing one Higgs boson and studying it. What are we talking about with these di-Higgs events?
Yeah, so di-Higgs means double Higgs, means producing two Higgses at the same time. So yeah, this is a bit the next big thing at the LHC. Because we're studying the Higgs in a lot of detail, but if we observe two at the same time, this is not just it's not just a coincidence of producing two particles, but we actually study a new fundamental interaction that we find very important. So as you can see on the right a bit of this Feynman diagram, you can see that that when the two protons collide and they radiate off two bosons, they can make a Higgs boson. And this Higgs boson in turn decays into two Higgs bosons. Well, that is a bit weird because if you have mass and energy conservation, you would say, like, how can you make two particles of 125 GeV?
Yeah.
If you start off with a particle of 125 GeV, but it's a quantum mechanical process. So you briefly produce one Higgs boson, which decays into two Higgs bosons. And this interaction, it's basically the interaction of three Higgs bosons at the same time. So if we manage to observe the two Higgs bosons produced simultaneously, we will learn about the Higgs self-interaction, as we also call it, or the interaction of multiple Higgs bosons at the same time.
Right. So we're interested in knowing how the Higgs boson bounces off itself, essentially, how it interacts with itself. Why is that such an important thing to understand? So people might not realize why, but so these collisions produce interactions between these multiple Higgs bosons. And why is that interaction between the three so important there? Why do we care so much about getting to that interaction?
Yeah, so the main reason is the is the Higgs potential. So
Yeah.
we always learn that the Higgs has mass. Yeah, actually, if you want to go to the previous one,
This
actually
one? Yeah.
that one, we always learn about the Higgs potential. We learn that particles have mass due to their interaction with the Higgs field, and that's because this Higgs field, which rolled down the potential over there, has a non-zero value everywhere. So we say like the Higgs is non-zero everywhere, and then it interacts with particles, and thereby these particles have their mass. So far, after 10 years of studying the Higgs boson, it seems to be correct that we're indeed in this minimum of the potential, and that this Higgs field interacts everywhere with particles. But we don't really know the shape of this potential, and we don't really know the origin. So the formula for this potential is actually very, very simple.
Yeah, I think I've got it.
Higgs wrote a paper about it in 1964. Brout and Angler came to the same conclusion also in 1964. And the formula is thus that the potential has a term with phi squared, so a parabola, and a term with phi to the fourth. So it's only two terms with two constants in front of it. Now you have to choose a minus sign between them, because if you have a parabola, you would just be always in the minimum at zero. So your Higgs field would be always zero. But by choosing the signs of the two terms opposite, you actually get this wine bottle shape, or this Mexican hat shape, or whatever you like to call it. and thereby you have this Higgs field over there. But this formula is super simple. The paper of Higgs was only like 2 pages. The mathematics was really not super involved. So you might say maybe they were lucky, or maybe there was something behind it, but so far we cannot really say that it is correct. Of course, within uncertainties we say it is in agreement, but we don't know if it really has this phi squared, phi to the fourth term. We don't know if there's, for example, more terms, or if it's different, and we also don't really know what causes this shape. So from to come back to your question.
So just for people who are watching, we see this beautiful wine bottle shape, but really all we know is that there's a kind of little bit of a parabolic shape around where we smash things together in our universe. So we wobble around this Higgs field around the bottom, but we don't really know what's going out over here or what's going out over here. This is our best guess, our standard model prediction of what's going on over at high values of the field, low values of the field, but we haven't actually measured that or inferred what it is. We just know about this shape around the bottom at the moment, and we'd like to know more.
And the formula that we see here is like a mu to the phi squared, which is related to the mass of the Higgs, and a lambda phi to the fourth, and this lambda is related to the self interaction. So if you go back to the previous plot, the previous Feynman diagram,
let's go back. This one.
So the interaction that you see on the right of the 3 Higgses, where 1 Higgs decays into 2 Higgs, this is exactly proportional with this lambda in the formula of the Higgs potential. So that is the self interaction. So you by studying the process of 1 Higgs decaying into 2 Higgses, you test the interaction of 3 Higgses with each other, and you directly probe this parameter lambda in this Higgs potential with your
okay. So looking at these interactions of 3 Higgs, they give a kind of parameterization. They feed into the shape of this. You can measure the shape of this parabola plus extra terms. So by looking at these self interactions, they give you a parameterization of the shape of that potential.
Yeah, that's basically what we do. And then if you fill in these terms, your equation over there, you see lambda 3 Higgs to the 3. So that basically tells you the production of the interaction of 3 Higgses with each other. If you expand it, you also get a term lambda 4 Higgs to the 4, and that gives you the interaction of 4 Higgs bosons at the same time. And what we in principle could do is say like, okay, are these terms what they should be, and are there maybe more terms, and are the terms that we measure, are they different maybe from what was predicted?
Yeah. So at the moment, we've got this wine bottle shaped prediction from the standard model, from Higgs's famous paper and other scientists' famous papers. But really, we want to make sure that that potential is the shape of that prediction, because at the moment we haven't mapped it and we're not sure that it exactly matches that standard model prediction. I guess if it doesn't, that points to the idea of new physics. Is that fair?
Yeah, and that is and that's why these, and because the shape of the Higgs potential and the Higgs field itself is so central in the whole way the standard model works, we now for the coming years at LHC Run 3, so we are collecting data now. We're in the third year of LHC Run 3, and the LHC is running full steam.
Yeah.
We get a lot of data, and we hope that then we can measure this lambda parameter more precisely, and hope to maybe learn something new beyond what the theory that was already that is already around since 50 years.
And why is this? Why is mapping the shape of this potential so important, Tristan? You mentioned obviously if there are deviations from it, that there could potentially be new physics. People talk a lot about this being important for the evolution of our universe, the distant past and the far future. Why is this potential so fundamental for the evolution of our universe?
Yeah. So I think for me there's basically like three reasons why this potential is so important and why we want to study it. It doesn't mean that if we're going to measure it that we directly get these answers, but it means it's really linked to various deep questions. But firstly, as a physicist, it's also like, what is the mechanism behind this? We have this potential in superconducting physics. There are similar kind of potentials, and there we understand what is behind the mechanism. So in condensed matter physics, for example, you have Cooper pairs, which means that this shape of the potential is basically made by electrons that are interacting with each other. So
we want to know the why, not just it is like that. We want to know how it became like that, maybe due to the dynamics of something underneath, like the Higgs is a composite particle or something else. Who knows?
So, but where did this shape come from?
Yeah.
And also, how did it roll down the potential?
Yeah.
We were in the beginning of the universe. Everything was massless. There was no Higgs field yet. The universe was very hot, high energies, high temperatures. And at some point, the universe was expanding. The temperature went down, and somehow this field rolled down the potential. So you might say, was there a cat who pushed the ball down the Higgs potential? But probably there was something else. And in the condensed matter physics, you have this kind of Cooper pairs. In the Higgs field, you could have something similar. Something that, for example, people said previously is maybe the Higgs is a bound state of top quark pairs, those kind of things. So that is what we also want to learn behind it. And then cosmologically, you would hope to learn something about the origin and the fate of the universe. When the universe was expanding, the Higgs potential was breaking everywhere in the universe, and this might have been a smooth process or a more abrupt process. So you could think of this as like as water boiling, where you create bubbles. So this breaking of the Higgs potential also could have created bubbles everywhere in the universe. And if we have a second order phase transition, as we currently have in the standard model, there's no such bubbles. But we believe we need such bubbles, and you need a first order phase transition there. But the standard model doesn't predict that. But we actually need this to understand why we exist. So also from there, we already believe or hope or think or feel that this potential might be different, and that maybe this breaking of the potential in the universe would have been different. And then
So I think just while we talk about that, I think some people suggest that maybe there was an initial bump that was needed to get over first, and then maybe this got the universe into states where certain areas weren't connected thermally to other areas and these kind of things, and you can develop these matter-antimatter asymmetries, for example, that we see in the universe today. So there's all kinds of deep questions linked to this Higgs potential. The way that the universe was and the way that this Higgs field was breaking, as you say, could really tell us how these matter-antimatter asymmetries developed, and essentially, as you said, why the hell are we here? This could give us a reason for that.
And very importantly, the current Higgs potential doesn't predict that. So I think it should be really different. Then I personally think the origin of the universe is very interesting. Then there's also sometimes people talk about the fate of the universe. They say, like, with the current particles that we know, we are in a meta-stable state, and that meta is, very meta, because it means that the lifetime of the universe would be 10 to the power 600 years. So, I mean, I like fundamental questions, but 10 to the power 600 years is not really my day-to-day worry. So that is, but it's also that at least it hints you that maybe there's something beyond the current theory that make the universe more stable, or maybe it is the way it is.
Yeah, people get very excited about that. The idea that this Higgs field, instead of just being a kind of parabola, turns over again, and maybe we could tunnel into this more stable state of the vacuum. But the likelihood of that happening is infinitesimally small. So don't be worrying about this Higgs quantum bubble coming to eat you anytime soon. It's probably not going to happen. But it's nice to get these any of these deviations and answer these big questions, as you say. So I guess as well, another reason to study these di-Higgs productions or multi-Higgs productions, I guess, is this idea of enhanced production, right? So if we study these di-Higgs events, I guess there's a lot of beyond standard model hypotheses that suggest these should be produced more than the standard model hints at, right? Is that fair as well?
Yeah. So at first sight, you say, like, okay, let's probe this phi to the square term, the phi to the third term, the phi to the fourth term, and see if they all match. But then if you see something different, this might be an effective coupling, but it might also be that the Higgs does interact with new kind of particles. I'm personally now more like, I don't want to take theories too literal, because we know from the past, as soon as we find something new, theorists often come with an explanation already. So we should go there directly, but it can be a hint. And there's quite some theories that say, like, maybe the Higgs or pairs of Higgses couple to new particles. So if we see a deviation in this self-coupling, which is then at lower energies, if we go to higher energies and we might produce these particles, we can actually maybe see them decay into pairs of Higgs bosons, and in that way we can maybe learn something deeper about what causes it. Current standard model has one scalar Higgs boson, but maybe this indicates that there's more additional scalar particles, which would then explain this new Higgs boson interactions, but also maybe guide us to a more complete theory.
Yeah. Okay, so lots and lots of things we can learn from these multi-interactions. Lots about the Higgs potential, potentially about new couplings, new particles, maybe beyond the standard model. So I guess the question becomes at the LHC, because we mentioned before we started this discussion, or at least before I started recording, that creating these events, creating these interactions is very, very difficult at the LHC. So how do we create these di-Higgs or more events, and why is it so difficult at the LHC?
Yeah, so that's actually quite fun. It's good that you showed these figures, because di-Higgs is a quite fun analysis. It's also very involved. We have many people now at the LHC working on it. it's not just because it's very interesting, it's also because it's very difficult. And we have these deep questions. But what you can see here is also that it's quite challenging, because on the bottom you see a process where you first have two gluons coming from two protons, which interact via a quantum mechanical top loop to produce a Higgs boson, and then decay into two Higgs bosons. This goes with this fundamental interaction lambda, which is in this Higgs potential. But then on the top, you have a process where you also produce two Higgs bosons. So again, they come just from two protons interacting with each other. It's not like we are at the LHC and there's simultaneously by accident two Higgs bosons produced, but they're really in a single proton-proton interaction. But in that case, the interaction of this very massive top quark radiates off a single Higgs boson and radiates off another single Higgs boson. So in one case, it's really a pair, and in the other one, it's two times a single one. And it mostly goes via this top quark because the top quark is so heavy. Now, the funny thing is, but also the unlucky thing is that these processes are already small, but they also interfere with each other, and they interfere with each other because they have the same initial state and the same final state, but they also interfere with each other with the opposite sign. So one process has a positive sign, the other one has a negative sign relatively, and they're almost of the same size, which means like you get process one minus process two, and
they almost cancel out each other.
They almost cancel out, so it becomes very small. So this means that producing a pair of Higgs bosons, besides the fact that it's more massive, so you need more energy for it, there's also this destructive interference, which causes the production of a pair of Higgs bosons to be 1,000 times smaller than the production of a single Higgs boson. So that is
So it's already a low statistics process to produce a Higgs boson in the millions of collisions at the LHC, and then we're taking another factor of 1,000 down in terms of the rate of producing these di-Higgs events.
Yeah, that's right. And I forgot what I wanted to say, but and then so we have to measure the total number, which is one minus the other, and then we can learn something about this little lambda over there. So we first want to see a pair of Higgs bosons, and then from this we can learn something about lambda, but it's a bit messed up by the other process. So we also have to make sure that we measure all the other processes precisely.
I think I've got a statistic here. So during run 2 of the LHC, which is basically 2015 to 2018, there was only 4,000, or the prediction of the standard model is that there should have been 4,000 di-Higgs events produced, compared to 40 million collisions that happen at the LHC every single second. So 4,000 in trillions and trillions of decays. So or of proton interactions. So very, very small rate. Very, very difficult to capture these things. And as you say, that's due to the low rate because of the interference between these diagrams. So please continue.
No, and I wanted to say, because then we come at the next problem. I don't know if you're gonna. I guess you're gonna show that now.
Come on, give us all the problems. Let's make it even worse.
We don't directly see a Higgs boson. We don't. The lifetime of a Higgs boson is 10 to the minus 20 seconds or something like that. So it's very short. So they decay, and the Higgs boson likes to decay to massive particles. So for example, the Higgs to BB process is quite common. It's like 58% of the Higgs decays. But the production of B quarks at the LHC is also a quite common process. So if you're gonna look for Higgses, you might be tempted to look for Higgs to BB. And indeed, you will find many signals there, but you will also find many backgrounds. So you also have to do a clever thing to see what is your the way that you're going to look for those pairs of Higgs bosons. There's many options.
So not only is this a low production rate, it's also hiding, as Tristan is getting at, in a background of proton debris and jets and all sorts of other things that are going on that could mimic that process as well. So it's not just there's only 4,000 to find in that data set, is that data set is also full of camouflage, if you will, for those processes. So they're very, very difficult to pull out. I guess the hope, Tristan, is that some of those beyond standard model hypotheses, there would be boosted production. So there would be enhanced production of these events, right? So maybe you would see more of these than you expect, which would make it a little bit easier to find them.
Yeah, but they are again also more rare, so it's all a bit of a trade-off. So we have to, in the end, well, for the experimentalists, the fun thing is that we have to gather evidence from all sides.
Yeah.
So the thing that you would preferably, or that you would naively do, is to say, okay, I'm going to look for Higgs to be B and Higgs to be B, because then you have 58% chance of a Higgs decaying to be B and another 58% chance of doing that. But then you also have a lot of backgrounds there.
Yeah.
Where you produce B quarks. So in the end, that ends up to 34% of the decays.
Yeah.
So we like to search for 2 times Higgs to be B,
yeah.
but it also means a lot of backgrounds. And actually those B jets, they also have relatively poor resolution.
Yeah.
And they're difficult to trigger. The resolution is typically 10% of the energy. So you have a bit of a smeared out signal. So in the end, this Higgs to be B and Higgs to be B is indeed quite powerful, but it's not the only thing that we do, because other things have advantages that cancel a bit. So,
okay. So this was the question I was going to ask. So you said these are very, very infrequent. So I was going to ask, how do you capture them? What decays of those Higgs do you use? And you're saying, yes, you can use this Higgs to BB. So the Higgs wants to decay to heavy things like bottom quarks, but looking for these bottom quarks in a messy hadron collider is quite difficult. So they might be the most frequent, but looking for 4 of these jets in all of the mess is a very difficult thing to do. So you're getting this trade-off essentially between how much the Higgs likes to decay into these things and how clean they are. Kind of, is it clean and easy to find? Does it happen often? There's somewhere in the middle where there's a good trade-off between those two. Is that fair?
Yeah. So, but there's actually, but there's no golden channel.
Yeah.
So there's many options that work a bit, but so for Bs, you have if you want to find a B jet, we know that the B lives a few millimeters in the detector and then decays into a spray of particles.
Yeah.
So you have to identify this few millimeters of lifetime and this spray of particles that are slightly different than the other spray of particles because they don't have this lifetime.
Yeah.
So that you have to do for 4 jets. Then you have a lot of backgrounds which actually do have this B jet, so they're backgrounds, but you cannot get rid of them. And then they have a rather poor resolution relatively because they are not so easy to reconstruct and also to trigger. So we have 1 billion interactions per second at the LHC, and we don't want to throw away the precious Higgs events, but these events for triggering, we always like to have, for example, electrons or muons or photons, because they're easier to see at the LHC. But at the LHC, we have a lot of gluons and B jets already. So triggering on these 4B events is also difficult. In that way, we have a lot of disadvantages. So we also try the other ones. Yeah. And actually, surprisingly, so if you're going to count and you would say like, well, Higgs to BB is quite large, 58%. Then what would come after that? Yeah, maybe W or tau or Z. Yeah. Actually, one of the most powerful ones turns out to be if you take one time Higgs to BB, and the other time Higgs to gamma gamma.
Ah, okay. Now, BB and gamma gamma. Okay, so you get rid of 2 of the jets that you have to trigger on, right?
Yeah, but the funny Higgs to gamma gamma is quite funny because
BB gamma gamma
photons don't have mass, so you wouldn't expect them to interact with the Higgs boson, but they do this indirectly via quantum mechanical loops. So you could still produce pairs of photons. And then the advantage of photons is that you can trigger them well. So almost all of them end up in the detector, and you can see them in a calorimeter. And the resolution is also very nice. Instead of this 10% blob of the Higgs to B, you have this. You have more like a 1% kind of resolution on the blob of photons. Now, the branching ratio of Higgs to gamma gamma is only 0.1%.
Yeah.
So one per mil. So it's like 600 times smaller than Higgs to BB. But as it turns out, so from the fact of the triggering and the good resolution, and also the reduction of the backgrounds, because much less of these photon backgrounds, somehow this kind of cancels out to each other, and the sensitivity of looking for 4Bs is similar to the sensitivity looking for BB gamma gamma.
Yeah.
So the 4B channel is very good, and the BB gamma gamma channel is very good. And but from the 4B, it comes from the high branching ratio, and from the BB gamma gamma, it comes from the resolutions and the efficiency. And in between, there's also BB tau tau, which turns to be also a bit of a, it has a bit lower branching ratio, but a bit better resolution and triggering. So those are all in the same ballpark, those three channels.
Very, very interesting. So you've got these ones that are very, very frequent to 4Bs, but they're hard to trigger on. There's low resolution. They're difficult to find. And then you've got these ones which are much less frequent, but they're easier to trigger on. They're easier to find. There's less background. So as you say, it kind of balances out in the end. So I guess when you're looking for these events, Tristan, do you kind of combine all of these channels together? I guess you look at all of them and then kind of try and lump them together in an analysis, take account of the correlations and these kind of things.
Yeah. So I mean, with the Higgs discovery, this mass of 125 GeV for experimentalists was a quite nice lucky coincidence, but because it turns out that actually at this point many branching ratios are sizable, which means that we can study many decays.
Yeah.
So for the single Higgs production, we can study Higgs to BB, we can study Higgs to gamma gamma, Higgs to WW, Higgs to ZZ, Higgs to tau tau. I'm even looking for Higgs to CC, maybe for a different episode.
You probably remember, Tristan, because we're of that age. You probably remember when we were studying before the Higgs was discovered, having these horrible diagrams of like the mass of the Higgs against the production ratios and where it could be, and there were lines going everywhere. And now we're sat at quite a nice position, as you say, in the mass where there are sizable branching ratios for all of these decay types.
Yeah, one of my former colleagues in CMS actually made a plot of all these branching ratios, and it turns out if you multiply all the branching ratios, which is a bit of a funny thing to do because it doesn't really make sense, turns out that actually at 125, it's a maximum.
Oh, wow.
And it looks like a Gaussian, which also doesn't make sense, but it peaks at 125. So it turns out that the product of all the branching ratios is maximal. So for experimentalists, it means we can study them well. So, and then we combine all the information to learn as much as possible about the Higgs properties. For the di-Higgs, we assume that this Higgs decays into two Higgses, where they subsequently decay into either B's or W's or Z's or gammas or tau, and then we combine again all these measurements to learn as much as possible about di-Higgs. Actually, what we also do, we don't just take this direct decays, but we also look at indirect information.
Yes. Yeah.
So from quantum mechanical loops, there might also be information about this self-interaction. So we also include those.
So they can be, just for people to, I don't know if there's a diagram of this in here. I think maybe this single interaction measurements, maybe they have a diagram, perhaps not. Maybe
I can do this very low tech, as I often on when I discuss with my students on Zoom. I just have a pen and paper, which is a bit old school, but
excellent. Good.
So if you want to study that, you can just look at this diagram, which means like you have one Higgs decaying into two Higgses, which then recombine again into a single Higgs, and there you have also again this self interaction that you can probe. So also from the single Higgs production, you can do that.
So for people watching, there should be small quantum corrections to these single Higgs events from these quantum loops that produce these virtual Higgs, and they pop into existence, then they pop back out of existence, but they give small corrections on these single Higgs events. So not only can we look at producing these di-Higgs physically, we can also look at their corrections in various other processes as well, and we can combine all of that information together to get the information about the couplings. Awesome. So the question becomes then, I guess, so we've talked about why this is important, what's going on, all these kind of things. What is the current status of this work? So my understanding, and please correct me because I could be very, very wrong, is we've not actually seen any of these events yet. We've set limits on how frequent these events could be. What's the current status of the Higgs work?
So yeah, define scene. I mean, we know that as you calculated, we know that we produced, according to the predictions, we produced a couple of thousands of them in the current data set. Currently, the limit that we set on the Higgs process is in the order of 3 times the standard model prediction.
Yeah.
So
the rate of production of these events can't be 3 times higher than what the standard model predicts. Otherwise, we would have expected to have seen it already. That's the kind of idea. Okay.
So yeah, indeed, exactly. So the rate is at most 3 times as large as is predicted. Yeah. Those limits we set at 95% confidence level. That means 2 sigma, which means that 3 divided by 2 is almost 1, which means that we have already a sensitivity of almost 1 sigma to the Higgs process. So we cannot claim a significant evidence yet, but in our measurement, which currently is very well in line with what the standard model predicts, we could have seen a few thousand of Higgses, except that our uncertainty is also of the order of few thousand. So we have almost a 1 sigma sensitivity, but it means we're not very far off. Yeah. So in run 2, we had a data set of 140 inverse femtobarn in Atlas. In run 3, the LHC already gave us 70 inverse femtobarn in 2022 and 23, and 80 inverse femtobarn already in 2024, which is currently still running. So we already have more than doubled our data set with respect to run 2. We also went to higher energy from 13 to 13.6 TeV. So we more than double the data set. We're at higher energy. We already have almost a sigma sensitivity. So we're getting quite close to really seeing it for the first time. Yeah. And then we have Atlas and CMS. So we are friendly competitors. In the end, we also want to combine our measurement. Actually, this is what we're still planning to do for run 2. So if we combine the data that we have from run 2 from Atlas and CMS, we will be already at the 1 sigma sensitivity ballpark. And then, we're actually getting quite close to seeing it for the first time.
And what about in terms of those couplings? What's the current status with that in terms of what we know about it?
Then due to this pesky interference thing, this destructive interference thing, then translating this first evidence of Higgs into a constraint on the self-coupling is
tricky, shall we say?
Not only tricky, but also it's a bit less sensitive. So if you look here, you should. So I think you can forget about the kappa 2v, but if you look on the x-axis on the kappa lambda, you can see that the inner circle of this inverse avocado is goes from roughly 0 to roughly 6. Yeah. So it means that we constrain a value of the self-coupling to be positive. We are excluding all the negative values, and then to be at most 6 times. Well, sorry, that is the 1 sigma interval. Or
so I think this for people who are watching, the standard model prediction is saying that it would be at 1,1. So the standard model prediction times 1 is obviously what we would expect. Here's the standard model prediction. And then here's what we're getting, which is some value, but as you say, with a large error avocado around it.
Yeah. So, I mean, if you look at the dotted line and you just look, if you draw a horizontal line at 1, for copper 2v1, then you will see that it intersects at roughly like 7 or 8 times standard model value. So this 1 sigma sensitivity to the di-Higgs process translates into an at most 8 times stronger value of the self-coupling. So seeing the di-Higgs is already difficult, but then the limit that we get on the self-coupling itself is even more challenging.
So very, very difficult to do. So according to our data, we can only say it's somewhere between what we expect it to be and about 6 or 7 times that. So lots and lots of room for potential new physics in there at the moment, because this is very, very difficult to see and very, very difficult to do. These results, can they tell us anything about those fundamental questions we talked about, or do we need more data? Do we need more information before we can start talking about things like the shape of the Higgs potential and the fate of the universe and these kind of things? Are we just at a stage where we need more information before we can say anything?
We always need more data.
Well, sure.
But at this, the good news, the limit here is not super stringent, but the good news is that for the self-coupling here, we really start to get in the ballpark where the theories start to make sense. If these couplings are very large, actually your theories break down because they're not longer unitary or perturbative or those kind of things. So your numbers that you calculate blow up to infinity, so your theory doesn't make sense anymore. We're now in the ballpark where they start to make sense. We're also getting in the ballpark where actually those theories of extrascalar bosons and electroweak baryogenesis, where they start to predict to have deviations. So we want more data, but already we're getting in the region that is very interesting. I personally think that for run 3, so we now had the LHC run 2, but for the run 3, with the more data and the higher energy, we will see for the first time the di-Higgs process. So that will be the big breakthrough of run 3, that we see this process. And for the HL LHC, so for the high luminosity LHC, so towards 2040, where we have 10 times higher brightness of the LHC collisions, then we can constrain this self-coupling down to an uncertainty of 50%.
I think that's exactly what the suggestions say. So if we go slightly towards the future, like you said, when we're talking about this high luminosity LHC, so that the next phase of the running of the LHC, the idea is to get this kappa lambda, as you said, down to this kind of 50% level where it could be double what the standard model predicts, but setting much tighter constraints.
Yeah, and then you should keep in mind that in Atlas and CMS we're always quite conservative. We make these predictions based on the previous analysis that has been published, and we always further improve things. I mean, we improve the trigger, we improve the reconstruction, like those boosted events or those beat tagging. We always improve them. So this uncertainty will definitely even be better than this. We can say something with an uncertainty of about 50% or maybe a bit better on this self-coupling.
Yeah, I guess that's something we've learned, right? Is over the last few years that we always do better with AI triggers and all sorts of new analysis techniques, and we always, fingers crossed, usually touch wood, do slightly better than this as well. So hopefully we'll go beyond these predictions.
If you put down the numbers, for example, for this Higgs BB events, there's so many that we don't trigger on or that we don't reconstruct correctly, that there's really a lot of room for improvement if we do better reconstruction. And indeed, machine learning, AI will also help a lot there. So that there's really a lot of steps to be made still.
So is that your prediction, that over the next set of running of the LHC, so talking about run 3 and talking about the high luminosity LHC, that we will see quote unquote, which obviously is a little bit subjective, but we'll actually have a physical di-Higgs event and also get down to these values on the coupling? Do you think those are
the
goals?
The official projections are based on the previous analyses, but and I'm an optimist, but many of my colleagues are now getting very optimistic, and I think most people believe that in run 3 we will see it. Also, Atlas and CMS are keeping each other on their toes, so
of course.
we always want to be the first. And the nice thing is that the Higgs discovery we did together, we both had 5 sigma, and now again we're both pushing each other to be good and be fast. So we're trying to get out something quite soon. But I think for run 3 we will together we will see this for the first time and really learn a lot here.
And I guess the development of those techniques for discovering these interactions is just worthwhile, even if we haven't seen one yet, right? Because these are going to be applicable for larger data sets, for future colliders, these kind of things. So developing all of that, all those detection techniques and analysis pipelines is useful upfront anyway. It's not wasted work, even if you haven't seen one yet.
No, that's definitely what we're gonna do for the coming decade to squeeze as much. The LHC does what it does. It's having fantastic performance, but then the job of the students is to try to make as most of it by improving everything that can be improved.
So looking even a little bit further into the future, Tristan, as we come to the end of this, where do we want to go after this? So if I talk about the infamous planned FCC, for example, how can we get a better handle on these di-Higgs events and these self-interactions, these self-couplings? Is this work for a future collider as well, where we can really go deeper into this?
So this is actually very tricky, and it's more difficult than you would hope. Because our plan after the LHC is to say, like, okay, we want to maybe build a Higgs factory.
Yeah.
Because we know the Higgs boson only for 10 years. We're studying it quite intensely already, but we want to go even a step further. So we maybe want to have a circular accelerator or a linear accelerator, or maybe even more fancy stuff. But for the self-coupling, it's actually very tricky, because for the self-coupling you need a lot of energy to actually produce them. You have to produce those 2 Higgs bosons. So if you build a Higgs factory, so the Higgs factory, like a linear E plus E minus collider colliding at 250 GeV, or the future circular collider colliding at ZH production of 250 GeV, then actually you're producing a lot of Higgs bosons, and you can do fantastic Higgs physics, but you're not producing those pairs.
So we're talking about HH rather than EE. So we're going even further into the future again.
Yeah. So if you're talking about the first upcoming project after the LHC, if that would be, for example, FCC, or it would be CLIC, or it would be ILC, if it would be the 250 GeV E plus E minus collider, then actually we're not going to learn so much about the self-coupling.
Yeah.
And that's why also this whole future collider discussion is very difficult.
Yeah.
Because we know that the self-coupling is fundamental, and it's one of the main targets after seeing the Higgs boson.
Yeah.
And it will be the main target of the HLAC. But the Higgs factory can do many things, but it can actually not outcompete the LHC. So on one hand, we want to run the LHC as long as possible in this high luminosity LHC phase, in order to squeeze out as much as possible on the self-coupling, because the next project cannot do that.
And then on the other hand, people want to move on to, we found this Higgs, I want to know its width and all sorts of other things and precision measurements and blah, 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 blah. So there's a tension there, right?
Yeah, but at this, if we just take the FCC-EE as an example, at the FCC-EE, we will be able to measure the width. We will measure the coupling with the vector bosons. We will measure the coupling with the second generation fermions. We will very much constrain the interaction with invisible particles, maybe dark matter, but not the self-coupling.
Yeah.
So and that's why many people also want to go even beyond this Higgs factory, to go, for example, to FCC-HH or the muon collider.
Muon collider,
Because then you do have the energy to produce those pairs of Higgs bosons, and then you can again learn something about the self-coupling. But again, yeah, this FCC-HH or a muon collider, that's even more ambitious than the Higgs factory. So you would expect that maybe a bit later in time, depending how optimistic you are. But yeah, so if you want to learn about the self-coupling, you either have to do it now at the HLHC, or you have to go immediately to the more ambitious future collider.
And that explains why it's become such a hot topic, right? With Atlas and with CMS and at the LHC. This is why it's important to do this work now.
Yeah, because it might be the only opportunity in our lifetime, and and that's why this discussion about future accelerators is very difficult, because we know that this self-coupling is very interesting. By the way, one thing that you might want to do at the muon collider, but which people also already doing, well, looking into in Atlas and CMS. I'm doing it with a student. We didn't publish it yet, but we know that in Atlas and CMS we're working on it, is to produce three Higgs bosons.
Yes.
So triple Higgs production.
Yeah.
So that's something that people have been considering for the muon collider, but I didn't want to wait for that. So some people already trying to do that at the LHC, and then you hope from the triple Higgs production. You start with one Higgs and you produce three of them.
So we got the quartic coupling now. Is that, yeah?
Quartic interaction,
right.
Indeed. So then you learn about the lambda 4. So that's something we didn't want to wait for the future, so that actually is coming also soon.
I assume that is incredibly suppressed at the LHC, right? There's no hope of.
So yeah, going from, I wrote the numbers down because I expected that question before. So if you go from single Higgs to di Higgs, you lose like a factor of 1,000.
Yeah.
You go from di Higgs to triple Higgs, you lose a factor of 400 again.
Right.
So we have millions of Higgses at the LHC. We have thousands of di Higgs, but we have a few of triple Higgs. But okay, you have to start somewhere, and sometimes you are lucky and you discover something new. So you also just sometimes have to just try it out.
Yeah. So there might be, like, in the Run 2 data, there might be like 10 tri-Higgs events or something. So good luck finding those.
Yeah. But very, then you play again this game where you have direct production of particles, but you also have the loops, and you have the trilinear interaction in the quartic. So you get all the processes next to each other. So it's actually quite fun also.
No, it sounds it. And as you said, with the muon collider put out these collaboration, put out these beautiful plots of, what will we be able to do with this, studying this Higgs potential by looking at these self interactions. They talk about what the high luminosity LHC will be able to achieve. So looking at the shape of this potential, and then the squeezing of that, the high resolution that you'll be able to get with a muon collider down the line. So as you say, there might be a break for something like FCC-EE, where we get these other colliders online later down the line. But it's a very exciting region of research, and people are really looking into it right now.
Yeah, and there's so many things, like, is this quadratic and quartic thing, what is the deeper mechanism, origin of the universe, fate of the universe? There's so many things coming in there that we just have to do it, and something might show up.
So I guess the final question I had, so do you think this work, looking at this potential thing, is a kind of key driver behind building larger colliders like FCC, HH, and muon collider? Do you think this is some of the work that makes that an extremely worthwhile endeavor to do? Because what I see in kind of public discussion of this, perhaps layperson discussion of this on Twitter or on YouTube, you'll see people saying things like, oh, they're just building these bigger colliders because they're hoping these new dark matter particles are going to turn up, or they still think Susie is there and they're just building a bigger collider to look for that, something that probably isn't there. Is this something that's a definite deliverable that we can get from these bigger machines, which makes building them worthwhile?
Yeah. So, yeah, some people are more optimistic than others, and some people say we should just build something to discover something. Other people say like, okay, can you just give me a guarantee of what's going to come out? So
Trying to do worst case scenario, right?
No
We can
lose
guarantee
scenario
a
is
bit of
always
this,
nice. And of course, when we built the LHC, the no lose scenario was that we would either see the Higgs or
something crazy is going. There's
we would know
something
that
there.
that there's something wrong with the standard model if we wouldn't see it. Yeah, I think for the Higgs factories, where the lower energy ones, where you just study the Higgs boson, you will definitely learn much about the properties like invisible particles, second generation kind of things. But then this high energy colliders, FCC, HH, or muon collider, there, yeah, the main thing is to really see this to probe this Higgs potential to its ultimate precision and learn about that. So that is the no lose guarantee I can give for
And
this.
if all these things start
Right.
popping out extra, brilliant. But there
And
is
of course, you always hope that that there's something new, but at least that is the guaranteed deliverable.
Awesome. Tristan, really, really interesting, really exciting work. Is there anywhere where you'd suggest people should go to learn more about this? I guess Atlas already has a really nice kind of Die Higgs page that explains all the latest results and why they're doing it, and a lot of this stuff about the Higgs potential. Is there anywhere else you'd suggest people go, or is this the place to look to keep up with this work?
Yeah, that depends also a bit like the media that you like, right? I mean, I think everywhere there's something to find. I mean, I
mean, obviously they should listen to our talk first. Like this is
definitely. But I mean, when I want to learn about other fields, for example, astronomy, I often get my information from Twitter, where I just follow other scientists or science journalists and see what the news that they have. But maybe Twitter is for old people. I don't know. So there's also people on TikTok, like my colleague Clara Nellist. She makes TikTok videos. Of course, you are on YouTube, and
you have a nice blog as well on New Scientist, I believe. Do you want to tell us a little bit about that? Get some people.
Well, that's slightly outdated. I did a few blogs a few years ago, but I prefer to talk to journalists and let them do the writing instead of do the writing myself. Writing myself is always a lot of effort. I mean, writing tweets is nice because it's short, and you give a link to the main news. But writing a whole blog by yourself, you get comments from the journalists saying that you should write like this, and that's too much effort. So I just prefer to talk to the journalist and let them do the writing. Otherwise, I don't have specific advertisements. I mean, you can follow me on Twitter, but I'm not mega productive. But I think in the coming years with the Die Higgs, that there will be a lot of news there.
Excellent. So I'll put links to all this down below. I'll put links to your Twitter, and head over there and find out more about this, because it really is a big and active area of LHC research, and it's only going to become more prominent with the next phase of the LHC, the high luminosity LHC. So Tristan, I'd like to thank you again. It's been really, really awesome. I've learned a lot. I think people will really enjoy hearing about this. And next time another one of these amazing results comes out, let's get back together and discuss what was done.
I think maybe like in 5 years we can meet. Then I think we will see the first Die Higgs. So then we should see if it actually matches the prediction.
Maybe before then, but I'm definitely going to hold you to that 5-year one as well. So that's good. All right, thank you very much, buddy. Have a lovely day. I know you've got to run for meetings soon. It's been a pleasure, and have a fantastic day and weekend.
Yep. Thanks.
Thanks, buddy. Take care. Bye now.
Bye.
Bye. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.